Hello, my name is Lao Yao Chong. This is the presentation for our distributed systems assignment. These are my group members. Max Liu Ji Ki, Regan Lim Lik Leong, Muhammad Segyo Amara, and Halim Ins. Then I'll be presenting the motivation behind our project. With the rapid growth of data from sources such as scientific experiments, social media, transactions, and Internet of Things devices, single machine data processing is no longer sufficient. These systems face limitation in storage capacity and computing power, leading to performance bottleneck. To address this, distributed data processing platforms have become essential. Cloud platforms like Amazon Web Service provide elastic and scalable resources to deploy such systems efficiently. In this project, we design and evaluate a distributed data processing platform on AWS using realistic workloads to demonstrate improvement in performance, scalability, and reliability. Our project focused on building a distributed workflow for astronomical image processing using Montage and HT-Codor. The goal was to efficiently process large image datasets by breaking the workflow into parallel tests that can run across multiple compute nodes. I'll pass to my next teammates.
So for our project, we decided to use Montage as our use case. What exactly is Montage? Well, it is a toolkit developed in 2003 to visualize astronomical images from fixed format into other formats, such as PNG and JPEG. At the time, it was able to automate image creation for lots of data and also integrate itself into workflows and pipelines. These are the things that other toolkits aren't able to do. Montage is split into various different steps: reprojection, resampling, rectification, and co-addition. Among those steps, reprojection and rectification, for example, are parallelizable. Or in other words, these steps are able to be split into different processes to process. Montage is a great tool for astronomy. However, it is still subject to its own challenges that needs to be resolved. First off, more data is going to be added over time, which makes the input data sets for Montage larger and larger, and in turn, it will create more intermediate files that require storage to store. Buying storage, especially, is going to be very costly. And finally, we need to set dependency constraints for consistency throughout the outputs. For our solutions, we need to develop a distributed system that share the same storage system and also supports parallel execution for efficiency.
Now, let's move into the architecture of our distributed system. To solve the problem of processing massive astronomical data in Montage, we designed a classic high-throughput computing HPC cluster. Our topology consists of three main layers: the master node, which is the control master, the working nodes, which are the compute resource that do the heavy lifting, and lastly, the shear storage, which implemented using NFS network file system. We choose this layout because Montage is data intensive. It requires multiple steps where output of one job becomes the input for the next. If the nodes can't share the files efficiently, the system breaks. At the heart of our cluster is the HD controller. It acts as an operating system for the distributed workload. On the master node, we run a collector and navigator. Think of the collector as a phone book. It knows which worker nodes are alive and available, while the negotiator is the matchmaker. They look at the jobs we need to run and match them with an available worker. On the worker nodes, we run StarTD daemon. They simply advertise the node availability, telling the master, I have 4 CPUs and 8 GB of RAM ready for work. When we submit a Montage task, HD Condor handles the logistics. We don't have to manually tell the node 1 to process image 1. The system handles that assignment automatically. However, computing power is useless if the workers can access the data. This is where our NFS architecture becomes critical. In a distributed environment, worker node 1 does not have the raw telescope image on its local hard drive. If you had that to manually copy file to every node, it would be incredibly inefficient. Instead, we mounted a share NFS directory across all nodes. When a worker executes a montage command, he reads the input file directly from the NFS server, processes it locally, and writes the result back to the NFS server. This ensures that every node sees a consistent state of data instantly. And finally, we have the workflow orchestration. Montage isn't a single script, it's a complex chain of dependencies. You cannot stage the mosaic until you have pre-projected the raw images. To handle this, use HDCondor DAGman, Directed Accolade Graph Manager. DAGman acts as the parent supervisor. It watches the NFS folder as soon as the pre-projection job finishes. DAGman detects the completion and automatically triggers the background matching jobs. This architecture allows us to fully automate the pipeline. We submit one file at the beginning, and the architecture handles the computation, data transfer, and dependency management until the final mosaic is produced. That covers up our architectural design. Now let's look at the demonstration. Go on.
Alright, so I'll be presenting my part on the lessons learned section. So yeah, in this final project, our team demonstrated that HDCondor and an NFS on AWS can enable parallel execution of montage workflows across multiple nodes. We learned that correct workflow logic alone isn't sufficient, where a properly configured execution environment is key. Early challenges arise from small configuration issues such as NFS bounds, file permission, and missing intermediate files, which cause jobs to fail, remain idle, or produce missing outputs. Systematic debugging using Condor_Q and Condor_status log inspection and verification of NFS bounds and permissions was critical in resolving these problems. We also identified the need for job dependency handling and pre-flight validation to prevent downstream stages from running prematurely. Reducing execution errors, effective group coordination was key, with team members sharing responsibilities for environment, setup, scripting, and debugging. Once the environment was stabilized, HDCondor efficiently distributed tasks and all core workflow stages such as image reprojection, background correction, and mosaic code addition executed correctly. This project confirms that a well-configured HDCondor and NFS platform provides a scalable, reusable foundation for distributed astronomical workflows and larger datasets. Now I would like to pass on the next part to the next person. Thank you.
To conclude, the HDCondor NFS platform successfully demonstrated distributed workflow execution for montage mosaic processing tasks like image reprojection, background correction, and mosaic code addition across multiple nodes. The system is reusable and scalable, capable of handling large datasets or more complex mosaics. We did observe some limitations. NFS bottlenecks affected intermediate data access. Some pipeline stages required manual intervention and error handling was not fully automated. For future improvements, we recommend automated pre-flight validation, better job dependency management, enhanced fault tolerance, and possible decentralized storage. Despite these limitations, the project shows the potential of HDCondor and NFS for efficient, high throughput distributed computing. Thank you.